Okay, thank you very much for the introduction and good afternoon. I am aware of my solemn duty as a pre-lunch presenter and also the last breakout session of the day to keep on schedule here. So I'll try to communicate what I have to say as quickly as possible and then accept some questions. So I'd like to talk to you about automated detection of asphalt road design surfaces for the purposes of automating construction progress monitoring. So why is that important to me? Well, from our research, we found that around $114 billion per year in global cost overruns is expected through the next 10 years just on transportation projects. And this problem shouldn't be surprising. It's been studied more than 40 times over the last 20 years, citing as many as 83 separate causes contributing to this inefficiency. And if you look at all those studies and all those various causes and you boil them down to the top 5 most frequently cited, this is what you get. And there's not a whole lot we can do about the first one, but the bottom 4 there I would submit to you are what I would call traditional project management type functions. So things that we can control by doing our job better. And one study identified that as much as 75% of cost overruns are attributable to factors such as that. And I would propose to you that if we're able to adequately monitor and control a project, we're going to improve performance in those other 3 areas there. So we've chosen to focus in on improving progress monitoring in the construction cycle as a means of addressing that inefficiency, that $114 billion per year. The issue is that the current practice for monitoring progress on transportation sites is still very manual, involves a lot of 2D drawings and red line markings on those 2D drawings. So there's an opportunity here to improve that process through automation, and a big step in achieving that automation of progress monitoring is to be able to identify automatically the different design layers of an asphalt road surface just within the digital as-built data. So a number of researchers have looked at similar problems to this, but they've focused mostly in building construction and almost primarily looking at structural elements like columns and walls. And there's some important differences there when you contrast that with the types of surfaces you get on like a road design. So if you're looking at a column or a wall, we're talking about orthogonally intersecting planar surfaces, whereas you look at a road, we're looking at much larger scale typically, and they change slope in the various dimensions. The other issue is that it's been almost exclusively all or nothing detection. So the column is either there or not. But if we're talking about detecting progress on road design surfaces, we need to get down to a more incremental level. It doesn't help me to say, yeah, that 500-meter stretch of road is now done. I need to know if it's on progress much earlier than that so that I can take corrective actions and get it back on schedule if needed. So if we're looking at incremental progress monitoring and surface detection here, existing methods are out there and they have promise for enabling an incremental approach, and I call them space partitioning approaches with our friend there, the voxel or the volume element, where we're dividing 3D as planned and as built overlaid space, and then we can query each individual voxel to determine the presence of as-built points and design model objects as well. Now the issue with the existing methods, think like an octree or just a blind voxelization of a 3D space, is that they don't fit the road design data very well. And to illustrate my point, I'll provide this graphic here. So imagine here we're looking at a cube, a 3D cube, but we're looking at it in 2 dimensions. And each square you see is a voxel of the same side length on each side there. And I have my traditional layers of an asphalt road here, and on the left, the YZ projection, think that as the center line of the road, just a small section of road. And on the right, the XZ projection would be the cross-section of the road design surfaces that you're looking at. So one thing I can see here, looking at the top on the left there is, and also on the right, point occupancy in a voxel alone in this case is not enough to say which design surface it is. So for example, if I'm in one of those upper voxels that has both the wearing and binder surfaces, just the fact that there's a point there doesn't mean that I can attribute that point reliably to a surface. Now I could voxelize at a finer scale, but then we're talking about, to distinguish between those layers, it's a 40-millimeter thickness between those on the road that we were doing our tests on. I need to get down to a really fine scale, and that then drives data collection methods that are more timely and expensive. And that's not the only issue. If I'm wanting to look on a per voxel basis to determine the presence of a design surface, I want a consistent framework. If I look at, let's say, the subbase on the far left, that surface is intersecting the voxel in the bottom half. If I look in the upper right, it's intersecting the voxel in the top half there. So I don't have a consistent framework for attributing points to that design surface, and that's going to cause some error in and of itself. So our goal and our objective in this small study was to develop a novel approach for fixing this. So we want to develop a data structure that's suitable for identifying incremental detection on those design surfaces on large transportation objects. We need to be able to identify the incremental part of that and then provide that consistent detection framework. And this is what we've come up with in order to do it. So this is kind of our overall process view. Our inputs are the design surfaces for each of those layered surfaces, and then the as-built point cloud data. And this is already registered just using commercially available software in the common coordinate system with the design surfaces. And we did that, you'll see later, using ground control targets. But it really kind of hinges on the generation of this brick tree. This is our data structure that we developed. So you can see the tree structure here, but it's probably a little more helpful for you to get a different graphic of it. So what we've done is we have a grid that we project below all the surfaces, and these are square grid cells in there. And then one of the parameters we have to deal with is this grid cell size. What is the size of each one of those squares? We project this grid up onto each of the surfaces, and where it intersects, we build a voxel there. So every time I'm building a voxel, I'm building it only where it intersects one of those, what I call raster branches, up off of the project grid. And then I have an additional parameter you see on the left, there's search distance, so I'm defining how far above and below that surface am I going to search to find as-built points to attribute to that surface. And that's something that we played around with in our experiments to try and find an optimal value. The additional threshold that we don't see here is what I call the point threshold. How many points have to be in a voxel before I can say, yeah, I think that the road is built within that voxel region. And again, that's another threshold that we played around with in our experiments. So once we've generated that data structure, an interesting question is, well, how should we construct those voxels? And there's a couple different options that we looked at here. Either segment-oriented, so in other words, when I'm building that voxel within the raster branch region, do I go in the normal direction from the design surface within that region? Or is it fair enough to say that roads are just mostly flat and I can just simplify the problem a little bit and treat it as a square block? And we ran through a number of iterations of that to determine that indeed the axis aligned is good enough. So the segment-oriented voxel ended up being more accurate, had higher performance metrics, but not by much. But the axis aligned was far, far faster. So we proceeded with that on our further experiments. An interesting problem that popped up for us was due to equipment and people and safety barriers on the surface. Sometimes we would end up with these raster branches where multiple voxels would be identified as being built. They all pass that threshold. And this was also due to random noise in the data. So the question was, well, how then can we distinguish which one it should be within that raster branch? And there's more sophisticated ways of doing this for sure, and we're going to be looking into that. But just for a proof of concept on the data structure, we looked at three different options. Maximum points, let's just pick the voxel that has the most points in it within that raster branch. Minimum variance, and that's measured in the normal direction from the surface segment within the voxel region. And then minimum distance, and we just ran through a number of experiments to see which one was going to give us the best results. So with that framework, we ran through 640 experiments. We were looking for that combination right there, which classification rule and search distance and point threshold were going to be best for us. The input data, I mentioned it before, we just used on the design side. It was AutoCAD Civil 3D design surfaces that we extracted as wavefront object files. You can see the layers there. There's a 520 millimeter thick subbase. All the way up to the thinnest layer there is the 40 mil thick asphalt wearing course. And that thinnest layer is important for this framework because it defines our maximum search distance, how far above and below those surfaces I'm going to search for points to avoid overlapping voxels. On the as-built data side, we flew Trimble's UX5 drone, and this was all done on a construction of a residential road for a new development in Cambridge in the UK there. We flew the UX-5, and you can see an image of the ground control targets that we used. We had 8 of those spread out across the site, and that was on the recommendation of Trimble's pilot on where to put those and the best layout of those. For the purposes of training before I get to that, we did use Trimble Business Center's aerial photogrammetry module for post-processing the data as well. And that gave us the point cloud with an average point density of around 340 points per square meter, so pretty good. And then an orthorectified mosaic image, which you see on the left there. And then for the training purposes, we just focused on that southern portion of the road because it contained kind of an interesting transition between 2 layers. On the bottom of this slide, you'll see the ground truth on that day. So as you walk the site, you would have actually been able to observe mostly asphalt binder course in this region, but they had paved 1 lane farther ahead than the other, which was the interesting part for us to look at. And then the rest was the binder course. And these are the initial results. So I'll let you kind of take that in for a moment as I describe the performance metrics that we see in the upper right in the corner. You're familiar with them probably. That's the standard true positive, true negative, false, all that. So the accuracy was kind of a measure of the overall performance, but it gives a little bit too much weight to those surfaces that are further away from the as-built data. Precision is of all those voxels that I recognized as being present in the scene, how many were actually present. And then recall is of all the voxels that I should have recognized as present in the scene, how many of those did I recognize as being present. So a lot of the errors, those are fairly low numbers on precision and recall. A lot of the errors were along the edges of the road where my algorithm, when I was building the brick tree, I was cropping the edges of the surface. So I ended up with some pretty small voxels on those edges where I just couldn't get the point densities that I needed. And that's something that we've addressed in further iterations, and you'll see in a journal paper that's coming up. But you can see the basic structure here, can't you? It's mostly asphalt binder course. You can see kind of in the curve there where that 1 lane is paved a little farther ahead than the other. And then we have some interesting errors that are suspiciously square-shaped and rectangle-shaped. And are there good reasons for that? And to find that out, we can just look at an overlay of the point cloud, and this is the asphalt binder surface as it goes through that area. And we can see that one large rectangular area. Well, that's because there was a van parked on the surface there. Okay, so that's explained. Talking to the contractors on the site, we ended up with a low area right there where a road was going to be constructed to meet up with it. And the contractor said, yeah, we typically build it a little bit lower on the binder layer so that when we pave that other road, we can smooth them together and make a smooth apron. So that was explained as well. A number of the squares that you see on the larger squares on the opposite sides, on the bottom towards bottom end of the road there, the contractor was going back and installing drain grates, and they had safety barriers up around those, so those were contributing to some of those errors. And then you see a lot of scattered and various single voxel cell regions that aren't picked up, and that's just due to inconsistencies in the point cloud. Either it wasn't dense enough right there, or there were some errors for whatever reason. So then we looked at, well, how can we correct for a lot of that, and can we do it in a reliable manner? So what we decided to do was just to do this outlier removal algorithm, where we're searching, let's say, within a neighborhood of the yellow cell that you see there, and you're looking down on the brick tree here, and you're sampling all the raster branches around the branch that you're looking at. You're looking at the classification of that branch. And if you have a consensus within that region, within the neighborhood, and that consensus does not match what the current cell being analyzed is, then you update it to that. So there's 2 parameters that we played around with there, and this is in the journal paper that's going into review soon, so it wasn't in the conference paper. The 2 parameters are the neighbor distance, how far do I search around that raster branch, and then the consensus threshold. Is it 50%? Is it 60%? Where do I draw that line to say if 60% was base course, then this cell should be base course as well? And these are the results that we got after running that. So you can see the performance metrics are much improved. We still have that structure between the 2 lanes, but it needs to be cleaned up a little bit. I'm not real good at identifying the transition between those different layers yet. But overall, the performance was much better. So to summarize here, it appears to be a viable framework. Certainly, this was very limited experimentation. I did this on one section of the road. The journal paper has the results of this applied to the other sections, and then to data collected on different days and data collected with LiDAR scanning as well. So look for that, and you'll see how these results generalize a little bit better. For future research, we really need to get better at delineating that transition between the design surface and the paving lanes. And then also, how can we identify those potential construction errors and differentiate them from just the random errors that we can just correct automatically, and then take that information to the project manager and say, hey, I think maybe we built this area a little bit low. Is that what you meant to do, or is this something we need to address? So thank you for your attention. 30 seconds over, so I think I owe beer to everybody here. So I'll take your questions at this point. Thank you very much.